imagine the following situation. We have a region of space. There's an electric field in here. We want to consider a circular path that starts at A and comes back to A. Okay? Now suppose it turns out that the electric field, we measure the electric field everywhere along this path with our little proton on a spring, and the electric field everywhere ends up being tangent to this path. So I can't draw it everywhere, obviously, but at this location, it's tangent to the path, and at that location, it's tangent to the path. Now this is a path where we can't take finite steps, so we'd have to take infinitesimal little dLs around here, okay, if we want to think about that. What I want you to do is take a moment and try to draw on a piece of paper an arrangement of charges that could actually make this electric field. Okay, you know a lot about distributions of charges. Think about a distribution of stationary point charges that could make an electric field that looked like that. Remember that it's tangent to this circle everywhere, not just at the locations I drew it, but everywhere in between also. So it's curly, basically. It's got this curl to it, okay? So think about the distribution of point charges that could actually make an electric field that looks like that. Any suggestions? Can you do it? Anybody? What? There's no object here necessarily. A coil, you have a charged coil, is that what you want? A charged coil? Well, that's an interesting possibility. So suppose we had a charged coil. Say they're positive charges. And so suppose we're here. Here's a positive charge. It would certainly make an E that way at this location. The problem is that there's another one over here that's going to make an E in the opposite direction. So that's a problem. It's not easy to think of one, is it? Okay, can anybody explain why it's actually impossible? What? Not because you need an infinite number of point charges. I can get a lot of point charges. Suppose we had this, okay? What would delta V round trip be for this path? Nick? What? Well, okay. Not the area. We've got a circumference, right? Let's see how we'd add this up. Here's an E, and so we take a little dl this way. Right? So we have an E dot dl, and notice that the angle, it's easier to use the cosine part evaluation formula here because they're in the same direction. So E dot dl is just E times dl, right? And here we have E that way, but dl's that way also. So we have another just E times dl. So this would equal the integral from 0 to 2 pi, well, 0 to the circumference, 2 pi r really, of E times dl. But the magnitude of E isn't changing the way we've set it up. So that's E times 0 to 2 pi r of dl, or minus E times 2 pi r. Does that equal 0? I thought we said it was supposed to equal 0. Suppose you actually managed to do this. What would happen if you took a little string and ran it around here and put a little sphere that was charged on it and let it go. So it starts speeding up and 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 speeding up, and it just keeps speeding up and speeding up. And are you putting any energy into the system? No. You just made a perpetual motion machine. You could be very wealthy if you could pull this off. But unfortunately, we've just proved that you can't do it. That what this really is an expression of conservation of energy, interestingly enough. And it says that you can't actually, by gluing down point charges and not putting energy into the system, you can't actually make a curly electric field like that. It's not possible. So we have actually ruled out, by looking at potential differences, we've ruled out a configuration of electric field. We've been able to say something is impossible, and it can never occur, that you could never glue down enough point charges to make a field like this, because you would be violating conservation of energy. And as much fun as that would be, none of us have managed to do that yet, except for, wasn't it Lisa Simpson did it? And she made a perpetual motion machine in one episode of The Simpsons. But other than Lisa, none of us has been able to do this. So actually, that's a pretty interesting consequence of what looks like a really innocuous statement.